So we come now to the Lorentz transformation. So let's set this up. Got a lot on the board here. We're going to go through it as usual, bit by bit, but I want to expedite matters and get some of the key things up here so I'm not just wasting time, as it were, writing on here. We'll have a lot of, this is probably the most mathematical series of video clips we'll do. Again, most of it is just algebra. It takes a little while to get through it, so we'll break it up into several video clips and make hay slowly, as is usual. And for those of you who, the algebra is very familiar to you, then you can obviously speed things up. So the Lorentz transformation. Let's just remind ourselves about Bob and Alice here. This time we'll have Alice stationary, Bob in the spaceship going at some velocity v. Of course, each of them have their frames of reference. Remember the props we've used before in terms of each of them, perhaps a spaceship, the lattice of clocks. So we can imagine Alice with a lattice of her clocks all synchronized, Bob with a lattice of his clocks all synchronized. Remember, in Bob's frame of reference, he's stationary. Alice is moving in the opposite direction behind him. Alice, in her frame of reference, she's stationary, and she sees Bob moving with velocity v in that direction. At the start, when Bob passes right by Alice, we'll assume that they start their clocks at that point. And so T sub A equals 0, T sub B equals 0. And we'll also have the origin for their measuring systems also to be 0 at that point. So everything matches up there. We'll get on to this in a little bit, this later at time T sub B, where we get a flash of light going on. But here's the basic question we want to try to answer. And that is, given the coordinates, space-time coordinates of an event in Bob's frame of reference, so xb, yb, zb, and some time T sub B, what would the coordinates be for Alice? xa, ya, za, and ta. In general, we'd like to go back and forth between the two coordinate systems. If Bob measures something and says, hey, I saw a flash of light, and it was at this location in my frame of reference, and this time, we'd like to have a relatively simple calculation so we can find out the coordinates of that flash of light in Alice's frame of reference. Clearly, we can sort of work through examples we've done before, but we don't want to have to do that every single time to work through the details, so it's nice to have a formula, and that's what the Lorentz transformation is going to give us. It's going to be similar to the Galilean transformation that we worked on before, so let's recall that. Simply that if we have two frames of reference in relative motion with respect to each other, inertial frames of reference, so constant velocity motion, and we'll use, again, Bob and Alice here, so Bob moving to the right, Alice stationary. If Bob measures something at coordinate x sub b and time t sub b, then Alice can find out where that is in her frame of reference by taking the x coordinate of Bob and multiplying by v times his time to find that out. And note the plus sign here. Think it makes sense intuitively because we know Bob is moving to the right. So if Alice is standing here, as Bob moves on, then if he measures something at 0, at his xb equals 0, we know Alice's measurement is going to be farther on in the positive direction because that's the direction Bob is moving with respect to Alice. And so it'll be whatever position Bob measures something at plus essentially the distance traveled by Bob in that given amount of time until he sees the flash or whatever happens to be. And then, of course, the y and z dimensions remain the same. They're not changing, and we essentially have ignored them in most of our examples, but to be complete, you could put those in here. And a key thing for the Galilean transformation is time was the same in both frames of reference. Now we know, we'll get over to the details of this in a minute, but we know right away that from Einstein's two postulates, we derive the fact that time dilation occurs and length contraction as well. So we know that this thing in particular, the time relationship here, is not true for the special theory of relativity when you get, certainly when you get higher velocities, but in principle for any velocity, as long as you have that velocity between frames of reference, there is an effect such that TA and TB are not equal. Again, as we've mentioned, it's so small usually in our ordinary everyday world, we don't notice it, but if you have very precise clocks, it is possible to measure that difference. So we know that the Galilean transformation can't work. We'd like to have something like this that works with special relativity. So that's our goal here. We'll get back to the stuff over here in a minute, but let's set up situation for Bob here and Alice. And what we want to do is later to time tb, so they pass each other at time t equals 0 essentially, and then later at some time tb, according to Bob's clock, he sees a flash of light right at his cockpit. So in other words, that is occurring at xb equals 0. Because remember, he's carrying along his lattice of clocks with him, his measuring system with him. As far as he's concerned, he's at rest, and Alice is going backwards there. And therefore, if he sees a flash of light right next to his cockpit, the x location for him, x sub b, would be 0 at that point. And we actually could then figure out where Alice sees that flash of light and what time, given the x location for Bob and the time t sub b for Bob. We could figure that out for Alice. In particular, one thing we'd use would be our time dilation equation. TA equals gamma TB. Remember, Alice is observing Bob's clock moving, and therefore time dilation will occur for Alice observing Bob's clock. Alice will see Bob's clock ticking more slowly and running more slowly, right? That's the whole idea of time dilation. Bob does not see any difference. His clock is working just fine as far as he's concerned. It's Alice observing the moving clock that has this Lorentz factor, gamma, involved in there. And of course, gamma 1 over square root of 1 minus v squared over c squared. Remember how we derived this? We derived this using the light clock, and didn't make a big deal of it at the time because it wasn't important then. But this was derived for Bob's location at 0. Okay, because remember in the light clock, we have it here, and we have our light bouncing back, going up and down. That's what Bob is seeing on his light clock. The light motion going up and down, the light pulse going up and down, is occurring at the same place all the time. Bob's just, he's got his clock right next to him there. It's Alice observing it, of course, moving along, so that as Alice sees it moving here, we'll squeeze this in, we get the familiar triangle effect. So Alice sees it going like this. But to Bob, all this is happening at xb equals 0. So our first time dilation equation really assumes that everything is happening at xb equals 0 for the person who is moving. And the Lorentz transformation we want, though, needs to be more general than that. Because, again, back here at the flash of light example, if the flash of light occurs right at xb equals 0, at Bob's cockpit there where he is, then fine, we can use our basic time dilation equation. But he might see the flash of light out here someplace. And therefore, we'd have a more complicated situation. And this will still be true in a sense, but we need to actually get a more general form of it. And we will see that once we get to the end result here. The Lorentz transformation will have some equations here that in the case for xb equals 0, when whatever is occurring, the flash of light, say, is at Bob's location, then this will still be true. But we're going to get a more general form of this type of relationship. Now, we also know, just as a reminder, the invariant interval equation. And this is true in general. And so this will be very useful for us to derive the Lorentz transformation equations that we want here. And again, it's just algebra, but it's useful to work through it so you can see where it comes from. It's not just magic. It doesn't appear out of thin air or anything like that. But it's a sequence of logical steps building on what we've done before. So we're going to start off just by considering, actually, in a minute we'll get to, in a couple minutes, we'll get to the flash of light out here at a general location. But let's just do the flash of light first at Bob's location there. So that's where we're going to head here and see what we get. So that's our general question. That's our goal. We want to, again, be able to transform back and forth there. And so we're going to start here with a couple things we know. Okay, so here's the situation again, later at some time TB, flash of light. We know, therefore, that flash of light occurs at xb equals 0, okay, at Bob's cockpit. What else do we know about that flash of light? Well, where does it occur for Alice? Well, Alice sees Bob traveling along at velocity v. We know we set up so they measured everything, the origin from when they were right together a little while ago, and then Bob traveled on. And so we can also say, if we say, just to indicate, this is the location of the flash to Bob. The location of the flash to Alice is simply going to be the velocity, relative velocity, times whatever time she sees on her clock, just v times ta. Okay? Now, here's the key thing. What is ta? Remember, we want to have sort of Bob's coordinates on one side and Alice's coordinates on the other. And so Bob measures the flash at time tb. We'd like to know, somehow write ta in terms of tb. Now, in actual fact, this is a case where our time dilation applies because we're talking about a situation where the flash is occurring right at xb equals 0 for Bob, sitting right next to him there. And therefore, we can just actually put this in here. Ta equals gamma tb, so this is going to equal, just put gamma tb in there. I'll put the gamma in front, because we often like to write the gammas in front. Gamma v tb. Okay, so that gives us some good information there. Therefore, if the flash of light occurs at xb equals 0 at some time tb, so Bob records some time tb on his clocks, then I can find out the x coordinate in Alice's frame of reference for that flash is just gamma times v times t sub b. So if Bob gives me that answer, or I take a photograph and look at his clock, observe his clock at that point, I can figure out the location in Alice's frame of reference as well. And then this would give me the time in Alice's frame of reference. Let's also, though, get this in another way using our invariant interval equation, because we're going to use this more here in a few minutes. And so just to show you that it does work the same way, let's just rewrite this. So we've got c squared, ta squared minus xa squared equals c squared, tb squared minus xb squared. That's our invariant interval equation. That's good for anything, basically, given ta, xa, and tb and xb for a given event, or distance between two events. In this case, the distance between the events will be our origin point when they pass each other, and then a while later the flash occurs, and Bob measures it again, t sub b and x sub b, and I want to be able to get the t sub a and x sub a from that. So what do we know here? We know, applying it to the flash of light right here, the flash of light occurs at 0. So that means this thing right here is 0. We don't have to worry about that. And so we're left with ta, xa, and tb in here, and of course c being the speed of light. And then let's also put in this, vta, for the flash of light. Again, that's Alice's distance for the flash, because it's just the velocity of Bob times how much time elapsed on her lattice of clocks. And so let's plug this in here for that. So we're going to get c squared, ta squared, minus v ta squared, just plugging that in, equals c squared tb squared. And advantage, of course, of these formulas is you just sort of, once you set it up correctly, you sort of crank through it here. And so note that, well, we'll do every step here. C squared, ta squared minus, this becomes v squared, ta squared equals c squared, tb squared. And when I think about that, I just have the times in there, just ta and tb. I've got a ta squared in both of these terms here, so let's factor that out. So that gives me a ta squared, c squared minus v squared equals c squared, TB squared. And now we're going to bring it up here so we have some more room. And so come up here. Now what I can do, let's divide each side by the c squared minus v squared. Okay? So I can write this as TA squared equals c squared over c squared minus v squared TB squared. You see what I did there? I just took this and really put it over on the other side of the denominator. Divided each side by this. So I got 1 here and c squared over c squared minus v squared over here times the TB squared. This becomes, for those of you who are up with your algebra, you might want to play around with this a little bit, see what we get here in a minute. So pause and if you want to do that and see what our final answer is going to be. It's going to be very familiar, but let's see what we get here. So let's do this. Let's factor out a c squared in the bottom. So I can write c squared times 1 minus v squared over c squared times TB squared. Okay, the reason I did that, well, first of all, I can do that. I've got c squared minus v squared, so I pull out the c squared, and then I've got v squared over c squared here. So this and this, they're the same things. The reason I did that, as you may see by now, is I can cancel my c squareds there. And so, where does that leave us? It leaves us with an equation like this. We get TA squared equals 1 over 1 minus v squared over c squared TB squared. Now we take the square root of each side. All our TAs here are assumed to be positive. We're looking at positive times, so we don't have to worry about when we're taking square roots plus or minus signs, as some of you may remember with that. So we get TA equals 1 over the square root 1 minus v squared over c squared TB. In other words, square root of TA squared is TA, square root of TB squared is TB, square root of this is this, and this should look familiar, I hope, right? This is gamma. So really what we've just shown is TA equals gamma TB. We started with this equation, with the invariant interval equation, and the fact that we are looking at a flash of light at xb equals 0, because remember, so we plugged 0 in here, and then work through the algebra, and lo and behold, what do we get? We get our time dilation equation. TA equals gamma TB. So that's good news, because if we didn't get that, we would have made a mistake someplace along the way, either here or perhaps in our earlier derivation of the time dilation equation using the light clock. Okay? So therefore, we say, okay, we've got this equation. That means Bob measures T sub B, and now Alice can, given that value on Bob's clock, again, take a photo flash, our old photo principle idea, take a photo of that, could see what's on Bob's clock, and if she, on her lattice of clocks that was at that location as well, took a photograph of her clock, this is what would be the reading on her clock. It'd be whatever was on Bob's clock times the gamma factor times TA, and of course gamma is always greater than or equal to 1, and so forth. And so you get the time dilation effect there. So given T sub B, then we know what T sub A is, but what about XA? What's the X location in terms of Alice's lattice? Well, I just erased them a minute ago, but remember we had this. We had XA simply equals V times TA. Now it's just the velocity of Bob times the time, elapsed time on Alice's clock. So she's watching Bob go by with velocity V. And therefore, this just is TA equals gamma TB. And so we can plug TA into here, and we get, this is gamma V TB. So that's XA. So now we have our two, sort of highlight them here. We've got that and that. That's a form of the Lorentz transformation for the case where the event is occurring at xb equals 0. Okay? And as we set up with the origins like that, which is standard procedure to set up the origins like that. if they're not set up like that, you can always, you can start your clocks at the proper time, or you can adjust the clocks. You can also adjust the clocks back and forth if you want to get a 0 point at that instant to have everything match up, and both Bob and Alice have their clocks at 0. Later on, of course, if Bob is moving, then they're not going to be synchronized anymore, as we've talked about with the relativity of simultaneity. But here's the Lorentz transformation equations for this case where the flash of light is occurring at xb equals 0. In other words, Bob says, hey, I measured a flash of light. It was at xb equals 0 and tb equals something or other. And then Alice could immediately say, okay, I know where that location is in my frame of reference. It's going to occur at time ta equals gamma tb. So Bob tells me t sub b. Alice then calculates t sub a. Got that? And also given t sub b, Alice calculates x sub a as gamma v t sub b. And so again, that's sort of a limited form of the Lorentz transformation for this special case. What we're going to do in the next video then is consider the case of what happens if the flash of light is not here as Bob measures it, but it's out here someplace at some general value of x sub b. So he'll have some value of xb for the event, this flash or whatever it happens to be, and the value of t sub b. And then we want formulas sort of like this, they'll be slightly more complicated, that Alice can use to figure out the time t sub a of that flash or event out here and the location x sub a. So that's coming up in the next video clip. On to part 2 of the Lorentz transformation. Let's remind ourselves what we just did in part 1. Again, Alice and Bob. Alice stationary in this case, Bob moving with velocity v, and each of them have their lattice of clocks synchronized. Now, of course, as we know from relativity, simultaneity, etc., that they would not be synchronized completely, but at time t equals 0, we can set up such that at that instant time as Bob passes Alice, then their clocks agree at that instant, and locations, we'll say, are at that the origin, the 0 point as well. And we showed for an event at some tb, some time tb measured by Bob on his lattice of clocks, and x sub b equals 0 at his origin point. In other words, with him in his cockpit, in his ship, we imagined a flash of light right there. So that means that's xb equals 0. Whatever time that flash of light may have occurred along here, if it occurred at his cockpit, that's where his origin is. Remember, that's his lattice of clocks. Remember the props we used that showed that lattice of clocks. And as far as he's concerned, he's at rest with his lattice of clocks, and that's the origin. That's the xb equals 0 point of the flash. And we showed, given that special case, then, and we know what Bob's time measurement is, we can find t sub a for Alice, what her time would show on her clocks, and x sub a, the location of Bob in terms of her measuring system. Now, what we'd like to do, instead of having the flash right there, as we talked about, we'd like to have a flash occur any place in terms of Bob's system that he measures. And he says hey, I saw a flash of light, an event, something occurred at xb equals something or other, and time something or other by my lattice of clocks. In other words, some xb, tb. And we'd like to find out, okay, for Alice, what would be the x location of that, and what would be the time showing on her lattice of clocks. So in other words, we need some formula. We want to have, given xb and tb, we want to say, okay, xa equals something or other involving xb and tb, and ta equals something or other involving xb and tb. Sort of like what we have here. ta equals something involving tb, xa equals something involving tb. xb does not occur in these formulas because, remember, the special case we did had xb equals 0. Now we want the general case where xb could be non-zero. And so we have to figure out, well, some formula, couldn't there be infinite number of formulas that might apply here? We'd like to put some restrictions on this in terms of what we're looking for. And just to give you a couple examples of restrictions. So we're not looking for just an infinite number of formulas. We have to sort through and figure this out. First of all, let's just say we had a formula like this. What if we said very simple thing. What if XA equals XB squared plus TB or something like that? Okay? Let's even throw a gamma in there as well. Just got some gammas around here. So what if the formula had that form? Given XB and TB, multiply all this stuff together, add it together, and that would give us the value for XA. Note this can't be the right formula because the units have to match up. XA is measured in meters or whatever length unit we're using. XB squared here, if we're using meters, that means this is in meters squared. You can't have meters over here and meters squared over here. And then gamma is dimensionless. It has no units. T is in time. It's seconds. And so I'm adding meters squared plus seconds. You can't do that. It doesn't make any sense. And so you've got sort of meters squared and seconds mixed up over there, and you have got meters over here. That's not going to work. You can't have a formula like that. So that puts some restrictions on it. In other words, whatever the formula is, the units for this one over here have to be units of length. And the units of this formula, whatever it is, have to end up being units of time there. So we can't have something like that. Another thing, I just actually erased our formulas here, but when XB equals 0, then I have to get my two equations from part 1. So these more general formulas have to reduce down to the part 1 equations in the case of XB equals 0. So that would be another restriction on it. But that still leaves a lot of possibilities. So we're going to it's not really a derivation here or a rigorous argument, but we're going to try to motivate a certain form of these formulas that we're going to have here to make our life a little easier. And here's the basic idea. If I'm writing, XA equals whatever over here and TA equals something over here involving XB and TB, I can't have any XB squareds or TB squareds or square roots or stuff like that over here. Okay? I just have to have XA or XBs and TBs in either case. Why might that be a restriction? If it is a restriction, it's good because it'll really reduce down the possibilities in terms of our formula, as we'll see. But let's just figure out why not? Maybe a TB squared in there or an XB squared or a square root or something like that. Let's consider our clocks here with TA and TB. And let's just say, let's let TA equals TB squared. Okay, now I know, as I was just talking about, the units aren't going to work there. So we'll assume we have some other stuff there where we can get the units to work out. In fact, let's do this exactly here. So, well, actually, I don't. We could do something like this. So that's seconds squared on the top. I need to get seconds here. So I need, in the denominator, I'd have to put something that involved seconds there. And so I certainly have a velocity. If I have sort of if you just play around with this, if I have a v involved there, velocity is meters per second. So 1 over the velocity is seconds per meter, right? And then if I multiply that just by, let's just say xb here. Okay, so xb divided by a velocity, so that's meters, say, divided by meters per second, gives me units of seconds down here. I've got seconds squared on the top, so the whole thing turns into seconds. Okay, so don't worry about it if you don't quite get the point there. The point being is I could make a formula over here such that I've got seconds here and seconds over there. But to make our lives a little easier, we're just going to assume that we're going to leave aside the dimensions and units for a minute and just say we can do something like this. TA equals TB squared. Just to show that we can't have any TB squareds over here. Why not? Well, let's think about this a minute. Let's say that Bob, okay, so we have TB equals 0, 1, 2, 3. Okay, just some times TB. That means by the formula we're trying out here, TA would be TB squared. So it's 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, by that formula, TB equals that, and plug in the values, and we get the TA values there. It's a little strange here. In fact, the point we're going to make is that the distances between ticks, say, on our clocks have to be uniform. Okay? Note the distance here. I've got 1, 1, 1. Here I've got 1, 3, 5. Okay? Why do they have to be uniform? Well, let's do this argument here. T sub b equals 0, 1, 2, 3. I could just as easily on Bob's clocks, we can also move clocks forward or back again, right? We can set them, we can calibrate them, just sort of like daylight savings time, or sometimes you do, depending on what time zone you're living in, what country you're living in as well, whether you use daylight savings time or not. But very easily you can recalibrate your clocks, set the origin, set the 0 point to whatever you want, and you're measuring elapsed times. It shouldn't affect anything. It shouldn't affect your answers in terms of when you set your clocks, in terms of the elapsed time between one event and another event. So for Bob's clocks, I could just as easily reset it and move it forward a second, so that instead of 0, 1, 2, 3, I had 1, 2, 3, 4. Okay, wouldn't make any difference to Bob in terms of his measurements. But look what happens when you then use this formula and put it into Alice's clocks and her times. Then it becomes, well, this is 1 squared, 4, 9, and 16. So whereas with Bob, the distances between the times between each event, still the same, 1 second, 1 second, 1 second. So I got 1 second, 1 second, 1 second. No change between if I had events at 0, 1, 2, 3 versus 1, 2, 3, 4. Just moving the origin for our time scale. But for Alice, it makes a huge difference that Bob just moved those over, because here I had 1 second between them, 3 seconds, and 5 seconds between those events. Now I have 3 seconds instead of 1 second, 5 seconds instead of 3 seconds, and 7 seconds instead of 5 seconds. So if I have things like TB squared in there and square roots and things like that, it messes up the timekeeping system. We expect that this transformation is such that you may have time dilation, as we've seen, so things get stretched out or compressed, but the distances between the events cannot change. Okay, so if Bob has 1 second between events, it's fine to Alice to maybe have 1.5 seconds between those events, but it's got to be 1.5, 1.5, 1.5 to match up with Bob's 1, 1, 1, or whatever the stretching or contracting factor happens to be. You can't have 1 and then 3 and then 5 and so on and so forth. So I realize that's a little bit of a hand-waving argument. It's not a rigorous argument, but that's what we're going to use here to say that you can't have any TB squares, XB squares, cubes, square roots, anything like that. So what this means is, assuming our little hand-waving argument here, we'll accept that. For our equations is something like this. And actually, let's write TA first. Okay, so it means that TA is going to take this form. It's going to be a so-called linear form. So for those of you who've had some math, either way back when or more recently, not really too advanced math, but certainly a little bit beyond algebra, perhaps, although you get this in algebra as well. All that being said, what am I talking about here? This is what it's going to look like. TA is going to have the form some capital G, we'll talk about what that is in a second, times XB plus H times TB, and XA, the formula for XA, again given XB and TB, is going to have the form M times XB plus N times TB. And as I mentioned, this is so-called a linear form because the XB's and TB's in the equations here are just XB and TB. You don't have any XB squareds, TB squareds, square roots, or anything like that. And what are the G, H, M, and N? Those are just, technical terms, coefficients, but they're just values that don't involve XB and TB. They may involve V and C, and they will, in fact, as we'll see in a few minutes, but not XB and TB. And so it's a linear form because technically these are forms of lines and not parabolas and things like that, and square root curves, et cetera, et cetera. So And that comes from our little hand-waving argument that the distances between times, and also works for distance as well, have to be uniform when you're transforming from one frame of reference to another frame of reference. It can be stretched or contracted, but it can't change from one to the next as you go along with it, as we saw. Okay, so accepting that, this is our form here. So this is the form of our Lorentz transformation equations that we're going to go with. Now, our final thing we have to do, and it takes a little bit of algebra here, but we need to figure out what G, H, M, and N are. And we can immediately start off with going back to the case if xb equals 0. So we know if xb equals 0 from part 1, we know Ta equals gamma TB, our basic time dilation equation for that special case. And we know that XA equals gamma V TB. Those were the two equations we came up with. And as we said before, these equations have to match these for this special case. So if XB equals 0, so this, if we take this and plug it into our equations here, that means, that goes to 0 for this special case. This term goes to 0 for this special case. And we know that XA has to, let's do TA first. TA has to equal gamma TB. So TA equals, this equals gamma TB. And XA, for this special case where XB equals 0, has to equal gamma V TB. So this equals gamma V TB. And lo and behold, immediately you can see what H and N are. And you've probably already seen it. If TA equals gamma TB and also equals HTB, clearly H equals gamma. Right? HTB equals gamma TB. So this implies H equals gamma. And for this one, XA equals gamma V TB, which equals N TB in our general form, linear form of our transformation equations, and therefore we have, this implies N equals gamma V. Therefore, here's what we've got. So the way we got this is we applied our special case, xb equals 0, to those general equations, and therefore we're halfway there, because now we can write, our general equations is this, we can write, okay, TA equals, we still don't know what G is, but G, XB, plus H is gamma, plus gamma, TB, and XA equals M times XB, plus N is gamma V TB. So those are our two Lorentz transformation equations. As I said, we're halfway there now. We still need to find out what G and M are. But we found out sort of half the form of the equations. We had the argument that they need to be linear like this. They need to, in the case of xb equals 0, reproduce our part 1 equations. And so we've got that in there. And now in the next video clip, what we'll do is tackle finding G and M. And we're going to go back and use our invariant interval equation to do that and crank through a little algebra and get our final form then of the Lorentz transformation equations.